Fellow mathematicians, welcome back to another video. I just came from downstairs, from under the table, I suppose. Gotta get myself some Hageromanchalik. No, we don't actually need this today. Let me take a seat. So guys, we did it. 100,000 subscribers. A tenth of a million subscribers and still growing. We are going ways, I suppose. Can't believe it. We have reached 100k subscribers. Today. On this very day. April Fool's Day. It's kind of annoying, to be honest, because I planned on releasing this video today, but I have already seen it coming. That it's going to be April Fool's Day. So I had to release my April Fool's video. So this is why there's a little delay between reaching 100k probably and this video. Nevertheless, thank you guys for everything. I'm going to say a few words at the end of the video. But what's the main point of the video today? This, my sons and daughters, is the main point of the video today. No, the title of this video hasn't been pure clickbait. This is actually an axiom where 100% of all the people failed who participated. It's not a joke, not even in the least bit. It's an anal 2 axiom, and yeah, everyone failed it miserably. Reaching those 100k actually marked the start of a new mini-series for this channel, and you can participate in this mini-series basically. So I went through my university and asked professors if they could give me axioms with the highest failure rate they ever had. And I ran across this gem right here. It's from let's just call him Dr. Professor K, Professor Dr. K at the University of Potsdam. And let me tell you something. This guy is someone who is extremely hardcore. He's one of those extremely hardcore professors. So here's a real-life example. So he's one of those guys who introduces Banach spaces in the first semester of mathematics studies. And one of the people there asked him what an example for a Banach space could possibly be. So in like the first 2 weeks of the studies he introduced Banach spaces already, which is ridiculous. And well, his answer was, well, the dual space of Banach space is a Banach space. Isn't that helpful? Isn't that really helpful? Yeah, I do think so too. He's just an absolute madlad. I love this guy. He's giving great lectures, but he's just extremely hardcore. So the next time I'm going to present to you extremely hard axioms where a lot of people failed, and somewhere across the video I'm also going to explain why probably so many people failed this axiom exactly. Here's the first one, anal 2. There's going to be more abstract algebra, theoretical physics or quantum mechanics, etc. So stay tuned. And here's the part where you can participate actually. If you have any axioms where a whole lot of people failed, like over 80%, send it to me, tell me the reason why so many people failed, and I'm going to present it here on this channel, so feel free to do so. We are going to dive in finally. Now, here's the German version. You have seen it at the beginning. It's pretty old, from 2005, and yeah, I have translated it for you. Actually, I just now finished transcribing it into LaTeX format. So just for you guys, I actually translated it for you. You can find download links to both the German and the English version down there in the description. If I have any typos in here, excuse me. Was a quick thing. So here's some background information for this very axiom. You had 4 hours of time to finish this axiom up. It consists of 13 exercises, 3 with a 10, and it's kind of ridiculous finishing this monster up in this short amount of time. This is already the first factor why so many people failed. Analysis 2, second semester. So second semester people had to do this. And the thing is, he packed a lot of functional analysis in here, which is already pretty crazy. Like I said, Dr. K is pretty crazy in general. Let's take a look at the first exercise. So the first exercise says that we have a sequence of functions which are continuous, so out of the space C0, and this line right here tells us that this sequence is actually Cauchy, this sequence of function. Cauchy in the supremum norm. It's a Cauchy sequence. And what you want to show is that there does exist some f out of those space of continuous functions, such that the sequence of functions converges uniformly to this very f. Okay? And also C0 goes from U to F, meaning both are Banach spaces, so U is just a
subset of a Banach space E. Now this is already the first problem. I think you have to take into account some properties of a metric here to actually finish this exercise, but this seems like a kind of standard exercise. Next one is asking if our C0 from U to F is actually a Banach space. If not, what are more conditions that we need to add to it such that it becomes a Banach space? And you have to give a thorough explanation for this. I do suppose it's not a Banach space, but I'm not certain about this. Next exercise, calculate the Fourier series of x minus pi squared over 4 on the interval 0 to 2 pi. That's kind of a standard exercise. I don't know if it really belongs into analysis 2 to cover Fourier series here. In my studies, we never covered it. So everything I know about Fourier series is just self-learned stuff. But this is the pretty not hardcore part. Next up, we want to show that each member of the Fourier series can be differentiated separately. Meaning if we were to have this Fourier series, so the series expansion, let's just say f, can be expanded, can you see it here, into a Fourier series, k starts at 1. Let's say we have those ak's. Then we want to know if f prime is del x in this case, let's put it like this, of this series is actually equal to the series of del x of those ak's. Okay, this is what we actually want to show. We want to see if we can basically point-wise differentiate everything. And well, in order for you to do this, what you really need to do is to check if this series converges point-wise. You can probably make use of Fourier's theorem or something like that and take a look at the point-wise convergence of a Fourier series. I think it should converge point-wise, I'm pretty certain about that. And also you need to show that the derivative f prime actually converges uniformly. This is what you need to do, I suppose, in order to show that this right here is actually true. From this, we want to show that pi minus x over 2 is equal to this series. And I shit you not, I have done a video on this before, so you can find the video to this in the description somewhere, okay? Where I have proven this to be correct on this very interval that we have right here. Also, from this we need to show that pi to the 4th power is equal to 9t times Riemann zeta of 4 basically. So yeah. Yeah, this is what we want to show also. So those are a lot of exercises, a lot of points on here. And this is pretty easy to show using Parseval's identity. I think he even gave it as a hint on the main paper. Yeah, you can use Parseval's identity for that. Next exercise becomes a bit more sophisticated. So we have V being a real vector space and the dimension of V is finite. We want to have an inner product defined and this inner product is being defined by its norm that is being induced on this real vector space, basically. So the norm squared is nothing but the inner product of X with itself. Next we want to have T to be a self-adjoint endomorphism of V. If you don't know what it is, we basically want that T goes from V to V, so from the vector space to the vector space is a mapping. And also what we want to have is that T is a homomorphism. That's what it means for something to be an endomorphism. And we also want it to be self-adjoint. So what does self-adjoint mean? If you ever done quantum mechanics, for example, self-adjoint means that in the scalar product we can basically change the way how we can use the operator T in here on what we have in the inner product. Meaning, if our T is self-adjoint, we can rewrite x, T being used on x as the inner product of T being used on x, x. Okay? So basically it's an Hermitian operator. Hermitian whatsoever operator. And from this we want to calculate the derivatives, that's the differential operator, so the first derivative, the second derivative and the gradient of our f that we have right here. It's kind of a standard exercise, but not too easy even, especially if you are under some pressure because it's an exam. Now the next one is one I don't really know how to solve up until now. So let S be this set right here. It's basically the unit sphere. So if we have this real vector space and show that there exists some x out of this S with f of x being defined as the supremum over all those f of y's and each such x is a unit vector of t. Don't know how to solve this up until now. It basically had something, it probably has something to do with the Jacobian also. I don't know for certain. Yeah, but this is number 3 out of 13. So if you are done with that, you got some points, but you are not even halfway done. Next up is something that I would actually be able to solve, even on an exam. Find a solution to this initial value problem. So we have y double prime plus 6y prime basically plus 5y is equal to t squared times e to the negative t. If you are wondering why he's using dot, Dr. Klein is an absolute beast when it comes to mathematics, and he's actually active in mathematical physics at the moment. So yeah, he's doing quantum mechanics and shit like this. So yeah, we have to solve this initial value problem on the interval 0 to infinity on the domain. And yeah, this is actually an exercise that you are able to do. So you just have to solve the homogeneous one, then you do some intellectual guessing basically, and then you are already done if you construct a self-auxiliary equation, or you use Laplace transforms. I mean, if he has done Fourier transforms before and Fourier series, then I'm pretty certain that Dr. K also did Laplace transforms. So this makes it even easier. Next up is another initial value problem. So those two are exercises where you can actually get points pretty easily. Find a solution on the interval 2 to infinity of x dot being equal to this stuff. That's actually not too easy. This one is, I think, a bit harder than this one up here, even though you get more points on this one, but maybe it's just because of the quotient that you have here. Or, I mean, it's kind of separable. The worst thing about that is actually that we have x up here for number 6. Illustrate the function, so meaning we want to have a 3D graph of some sort. Okay. Illustrate the function f of x in the neighborhood around its 0 using a topographical map with contour lines. Meaning we want to have some of this, like, I don't know, I can draw for shit. So we want to have something like this, okay? We want to have a topographical map, like a contour map with those height lines basically in here. So where you have to mark, for example, singularities and stuff like this. This in fact doesn't have any singularities, but I hope you get the point here. So you have to draw this at first, gets you 3 points. I think that's cool. This next exercise is one that I do not understand. I have no idea how to solve this. If you have any idea, please tell me down there in the comments. How is this map different from one of a function g, which is infinitely often differentiable, from R2 to R, where we have an initial value problem, where the Hessian matrix d squared f of naught has 2 eigenvalues. One is greater than 0, one is less than 0. I have no idea. Tell me in the comments if you know what this means. Take a look at the German version, maybe you can get a kick out of it, and maybe tell me what this is all about. And the last one is, why is f called a monkey saddle? Because it looks like a monkey saddle. So if you take a look at f actually, this thing is called an ape saddle just because 2 parts actually would go over the shoulder, and then we have this part on the back, and the last part goes over the bumps here. Okay, that's why it's called a monkey saddle. Take a look at Wikipedia, there's actually an article for that. Next one. We have a mapping which goes from R2 to R2, and it's given by this vector right here. And we want to find a set M of all points in which f is locally invertible. You check for local invertibility by taking a look at the Jacobian matrix and the determinant of the Jacobian matrix, basically, of this thing. Jacobian matrix, so that's the determinant of del x, and then once again del x, del y, I suppose. I always forget the order in which is in of those components that we have right here. So we have like f1, f1, and then we have f2, f2. Those are the components. You check if this is not equal to 0. So this is like inverting a matrix basically. So you take the Jacobian, and then you want to see if the determinant is not equal to 0, and then you actually check for local invertibility. And now we need to see if it also has a global inverse, so where f goes from m to f of m. So yeah, it's kind of the same procedure. There's for the global invertibility, I'm not certain. There should be some kind of other restrictions that you need to take a look at. I'm going to put an annotation somewhere here in the video if I have more clues about that. Now we have an interesting exercise, which I find to be quite attractive. Now we have some function f out of the space C1 from Rn to Rn. So this is the space of functions with which are continuous and differentiable, and where the differentiation is also continuous. And we have a norm induced on here. So the norm of the derivative of f is bounded by some c which is less than 1 for all those x out of Rn. And now we want to define ourselves some g, which is x plus f of x. This is kind of like a shift. And we want to show that our g is surjective. Not an easy exercise, but a real fun one. Try it out for yourself. Now next one makes use of the implicit function theorem. Show that this function, which we have in 3 variables, can be solved for z in the neighborhood of the point 0, -1 and 1. So you have to see if we can actually solve for z on here. Yeah, you can do so. And if you have z in terms of x and y, this happens if you solve for z being thus a function of x and y, we want to find the partial derivatives at the point 0 and -1. Yeah, kind of an easy exercise, but a pretty good one. Here comes the real messed up part. So we have a function in 3 variables being defined by those arctangent, cosh, and the tangent, and we want to calculate its Taylor polynomial of the 3rd degree around 500. This has to be an absolute joke. I mean, the multivariable Taylor polynomial or Taylor series is not too bad if all of those parts in here in the variables are actually separated by additive stuff, plus and minus, but the thing is, cosh and the tangent are actually in composition with each other using our multiplication. And this is kind of bad, so you have to make use of the gradient and you have to do this 3 times and it's kind of messed up. So this exercise takes quite a while looking at it on the first glance. So this is kind of a monster, and I would do this somewhere at the end. I wouldn't do this at the beginning. It would just take too much time. Next up, if you ever did nonlinear dynamics, then you probably did something like this before. You have to calculate the stationary points of this function on the set S, where all the x's multiplied together are equal to 1, and each of those x's is strictly greater than 0. And you have to determine the type of stationary points. Okay, if it's stable, if it's unstable, etc. Asymptotically stable, blah blah blah. And from this we want to deduce the GM-AM inequality. This is an extremely cool exercise, and it combines so much of analysis 1 and 2. Try it out for yourself, it's a really good one. Next up is something really cool. I have done it after the first advent calendar on my channel before. We have some matrix which is positive definite and symmetric, and we have a scalar product, an inner product given here. Now we want to calculate this generalized Gaussian integral that we have here. Take a look, the link will be down there in the description. I state all the stuff there that is important to solve this exercise. Take a look at it for yourself. It's something that pops up in quantum field theory a lot, so that's an amazing exercise. Try it out for yourself. Okay, it's pretty cool. And now for the last exercise. The axes of 2 circular cylinders of the same radius intersect in a right angle. So if you don't know what that means, we have our first cylinder here. Can you see it? Yeah. And then this is the axis. And now we have the axis of another cylinder. Okay? And they both have the same radius. Okay? I hope you can see where this came from. And now we want to calculate the volume of 2 cylinders intersection. Meaning overall, we want to calculate the volume of this thing right here. So you can think of it as 2 pipes intersecting. I think each and every one of you has seen something like this before and what this exercise means. And after that, we want to calculate the integral over some region A, where A is the set being enclosed by the parabola x squared and the linear function x plus 2. That's a cool exercise. I mean, the main point here is to find out what the upper and lower bounds actually are, or you do a change of variable and you use the Jacobian matrix right here and the determinant. And this has been the Analysis 2 exam by Professor Dr. K. Now, why has it been such a hard thing to do for most students. There must be a reason. 100% failure rate is pretty critical, and it only happened 2 times at my university. One in numerical analysis, 2, and once on this one right here. Well, thing is, so in a normal case, someone else does the tutorials and the homework stuff. Her name is Dr. R, let's call her this. And in a normal case, she is designing the exams for this class, or she has been back then. But at one point, Dr. K said, no, I want to design this one. And yeah, he came up with this exam like 1 hour before the exam actually started. He hasn't calculated through anything. Dr. K is someone who gives at least 16 to 26 homework assignments each and every week. No one can actually do this. It's absolutely ridiculous. That's why I said it's absolutely hardcore taking a course from him. Yeah, and well, he actually finished this up late, this exam, so finished typesetting it late. So he came like half an hour later to the exam and handed out everything. Everyone was waiting already. So everyone was on edge already. And yeah, well, everyone failed because no one was prepared for such a hard exam. No one knew that something like this was coming. And I suppose that Dr. R didn't even introduce Banach spaces and stuff like this at this point in time. I'm not certain about that, but Dr. K is also someone who loves to introduce stuff in exams that no one has ever heard of before. So in one of his exams he also introduced Hausdorff spaces and stuff like this, and the students never heard of it before and they had to calculate something with it. I mean, if you study mathematics you should be able to do something like this, but it was pretty hardcore. And that's basically the reason why everyone failed. They were just pretty unprepared for such a hard exam. And this is it. I hope you did enjoy what I did here today. I'm going to make at least 3 more videos. If you want to see even more, send me exams that you know about where a lot of people failed. And here are some end words because, you know, 100K. So, I would like to thank each and every one of you. Seriously, guys. Even though I have been hacked, everything, even though we had this drama with Black Pen, Red Pen, stuff like this, you stayed here as a community, and I would just like to thank each and every one of you, and I hope you are going to stay with this channel a lot longer. As you might have seen, I'm polishing up everything on this channel right now, be it the outro, the intro, etc., putting animations into here, trying out some new formats. I'm trying to improve the quality of each and every video steadily. And yeah, I can just do so. So the sole reason why I can do so is because of your support, and I can't thank you enough for it. Thanks to all my Patreon supporters, the people who spend so much money on this channel because they enjoy the videos to such an extent, and I'm buying new equipment each and every time for the channel, and can't thank you enough. Thanks to all the members of the channel who were so kind to join as a member here, and also thanks to everyone who's buying my merch. I for myself really love my merch. I'm running around with the stuff too on the streets, and it's just amazing to know that we have sold over 1,000 products up until this point. It's so amazing to know that 1,000 people at least walk out there with Papa Flammable. It's just so weird to imagine. And yeah, a few more honorable mentions go to all the people here on YouTube, other creators who supported me along the way. I would like to give a special thanks to Black Pen, Red Pen, so Steve Chow, and also Dr. Payem. Even though we had those differences, even though we don't talk to each other, I just want to let you know that I'm so thankful for everything you have done to me. No, you have done for me, not to me, for me. I'm just thankful for everything, and don't think that I have anything against you. It's nothing really. I don't mind you guys, and if you watch this, feel free to shoot me a message. I don't have anything against you guys. You guys are pretty cool, and you do some amazing content here on YouTube, and I can't thank you enough for supporting me along the way and for giving me shoutouts, etc., collaborating with me. Speaking of collaborations, I would like to thank Tibbies, Andrew Dodson, John, Sexstar, all the other people who participated on Math Vengers, for just being there, for supporting me, for actually shouting out on Twitter when my channel has been hacked, and etc. pp. Can't thank all of you guys enough. And yeah, next real subscriber milestone is going to be 250k for me, just because pyrocynical. I never thought that I'm going to reach this milestone at some point, and I can't resist doing this. So guys, we did it at 250k subs, so be prepared for that. Let's see when we can reach it. If you did enjoy this video, please like and subscribe and recommend channel. If you like, share this video around if you really did enjoy it, if you think this format is something that we should do more on this channel. And yeah, thanks for everything. 100,000 subscribers, it's absolutely amazing. And yeah, I can't stop smiling, it's just so cool. It's such a milestone for me, it's just ridiculous. Up until the next video, have a flammable day. Ciao.